All right, it's working. It's working. See, you're clearly excited about that, Danny. All right, hey, yeah, 5.2, we're going to start looking at what we call central angles and arcs right here today. Goal-wise, you're going to be talking about 3 formulas and understanding their meaning and what they have to do. So a little bit of vocab here today and some formulas. This section is really pretty easy. Now, I will tell you today, you're going to be at a very, you'll have an advantage if you put stuff in radians today. Okay, so you might want to make a note that if stuff is in radians, you're going to be in good shape. So in this section, 5.2, you might just jot down that radians are good. All right, radians are good. Okay. One thing I'm not going to get too excited about here is the linear velocity one down here. I'll show you what that formula looks like here in a second, but I'm not going to get too excited about it. What I'm really worried about today is central angles right here and arc length. Okay, so let's talk first of all central angle. Central angle is basically an angle within a circle where the vertex of the angle is the center. Okay, so central angle because our vertex of the angle AOB right here. Angle AOB is going to be considered a central angle because the vertex of the angle is at the center of the circle. Make sense? So you understand what a central angle is here? All right. So right here then, guys, the second part of this is an arc length. Now they give you a nice formula for arc length, but what the heck is arc length? Well, arc length is going to be any arc on a circle or a part of the circumference right here that's marked off by my central angle. Okay. So which arc is angle AOB really intercepting for us? A to B. So this angle AOB really is talking about this arc length right here. Okay, so that's the arc length that's marked off by your central angle. Okay, so a central angle really defines what your arc length is going to be. Okay. All right, so I want to show you something real quickly here, guys. Really, what's the arc? Well, I shouldn't say this right here. What's the measure of the central angle, really? How many degrees is that? 80 degrees. So you might want to make a note here. This is a central angle. This angle is 80 degrees for angle AOB. All right, that's marked down here. Okay, so if they put the 80 down here by the arc, or if they put the 80 in the center of the circle, just know they mean the same thing. So would you agree that this x is really equal to how many degrees right here? 80 degrees. So you might want to jot that down by this diagram. That x, that value there, x is equal to 80 degrees. Now again, I think I told you in the last section, anytime you see a theta, anytime you see the Greek letter theta, that typically is a Greek variable for unknown angles. In this case, I put in x in here, but most times, what are you really going to see in there? Theta. Okay. Let's talk about arc length. They give you a nice little formula here. They say the arc length of a circle, or the distance marked off here like in green, for any arc is going to be defined as S equals R times what? Theta. The big idea here is that theta needs to be measured in what? Radians. If I'm going to use that formula, S equals R theta, theta needs to be in radians. You guys remember how to turn degrees into radians? Yeah. Times pi over 180, right? Okay. Let's talk about what the other stuff means right here. In arc length right here, you might want to write down S is going to represent the distance of the arc. Okay, so S is going to represent the length of the arc. How long is that? It's like saying if I could take this green part of the circle, cut it out of there, and then pull it flat, what would that measure be? Okay, so S is going to be the arc length, the actual arc length. Anybody got to guess what the R is for this formula? Radius. R is going to be the radius. Okay. And then theta is going to be any angle as long as we measure it in what? Radians. Okay. I want to jump into an example involving arc length here real quickly. Okay. I'm going to talk about a circle here quickly. You may or may not want to write this down, but just pay attention as to how this comes about. Okay, here we go, kiddos. This is what I'll tell you. I'm going to draw me a circle here. Okay, it's a nice circle. And in that, I'm going to put in a central angle. It looks like that. That looks pretty central, doesn't it? Pretty good. What's that angle appear to be? 90 degrees. Okay. I'm going to put a radius in here of about 7 inches. Okay. Now, guys, would you agree that this central angle right here marks off that arc right there? Okay. Well, watch this right here. We're going to kind of talk about this without radians and without formulas first and try and figure out that arc length. If I had to say, guys, I want to know the distance of this part of the circumference, what might you do? Do you have formulas to find a whole circumference, first of all?
Yes.
Pi times diameter or pi times 2 radii, right? Or that's where that formula, the number of radians, is coming into play, right? 2 pi radians in a whole circumference. You guys got thoughts on how you could find that distance right there? So find your circumference and divide by 4, because 90 degrees is what fraction of a whole revolution? It's a fourth of it, right? I totally agree. Okay. Another thing I might be able to do is say, well, you know what? How big is this central angle? 90 degrees. That's part of a whole revolution. How many degrees are in a whole revolution? I could say 90 is to 360, which coincidentally reduces to which fraction again? 1/4 again, right? Okay, I could say 90 is to 360 as my whole, well, the arc length is to the circumference. Isn't 90 part of a revolution, part of a whole revolution? Isn't the arc length part of the whole circumference or whole revolution? You guys understand this proportion I've just kind of set up right here? I'm comparing part angle to a whole circle angle-wise. Comparing part of the circumference to the whole circumference. Part to whole, part to whole. Could I set a proportion up here? Do I have enough information to figure out what the whole circumference would be? Who's got a calculator handy? My circumference would be pi times diameter, right? What's the diameter across
14.
here? 14. I can take 14 times pi, which I believe is, oh, is it 43.96? Something like that? 98, 43.98. So that's circumference. If I take this circumference right here and go 43 times, I'm sorry, 14 times pi, right? What did you get for a circumference again, Cole? 43.98. Well, guys, that would mean that the whole distance around the circle is 43.98 inches, right? Sans idea, give me a fourth of that value now. That'll give me the arc length, right? Or if I wanted to set up proportionalized, saying this 90-degree arc, or this 90-degree central angle in a circle marks off an arc of a whole circle circumference 43.98. Somebody solve that for me. 10.9. 10.9? Okay, so this distance, this arc length, how much again? 10.995, so I'd probably round it. Can I make a rule in here when we get ugly numbers? I usually go 2 places, okay? So I'm not going to get picky on places, but I usually go 2. So if it's 10.995, I'd round up to what? 11. Okay, so about 11, right? Well, on that first page of your notes, we said that there's a nice formula that says the arc length S is equal to my radius times what? Theta. Keeping in mind that theta is measured in radians. Okay. Let's just do this quickly. Let's talk about this. First of all, let's convert this angle measure to radians. So theta would equal my 90 degrees that we have. How am I going to convert that into radians?
Pi over 180.
Times pi over 180, right? Guys, do you agree that 90 over 180 really reduces to 1/2? So this is really pi over 2. So in this case right here, this 90-degree angle in degrees is pi over 2 radians as well for the central angle there as well. Would you guys agree with that? Okay, so now here's the situation, guys. I just told you on the front right here that the arc length of a circle can be my radius times the angle in radians, okay? So we know the answer is going to be about what right here? 11. We deduced that. We said, you know what, here's a quarter of a circle. We understand why this is 11, right? Okay, let's see if this formula holds true. My arc length S equals my radius. What is the radius in the given situation? 7 times theta, which is what? Pi over 2. So if I pull this out here and say, well, let's punch that up and see what a good arc length would be. That would go 7 times what? 7 times pi, and then divide that by what? What do you think? Match what we had? Okay. So when I come back to my notes right here and say, what's the formula for any arc length of a circle? You're simply going to tell me it's your radius times what? Theta, where S represents the arc length, but you've got to make sure R is with a radius. You'll also need to know that theta, this is very important, right? It has to be in what? Radians. If they give you degrees, you got to convert, right? I'm not going to get too concerned about linear velocity. We'll come back to that a little bit. The other one that I'm really concerned about is area of a sector. I'm not going to confirm this with you. Just take my word for it. But the area of a sector here says your area A is equal to 1/2, which I would probably turn to, I think for punching stuff in purposes, call it 0.5. Is that fair? 0.5 r squared times what? Theta. Understand that arc length is a distance around here, right? Okay, how about area of the sector? What are they implying there? Area of the sector would be the number of square units inside of this that make, oh, I didn't want that. Give me a square, come on. There we go. The number of square units on the inside of that sector. How many square units fill up that sector right there? Okay, so that formula right here, 0.5 times your radius squared times theta. Again, theta in what? Radians. Okay. All right, first side notes, any questions? Okay. What's going to be to your advantage here in this section? Angles in radians. Okay, let's jump to the next page here quickly, kiddos. By the way, what time did we get out of here today? 45, and my gosh, time flies when you're having fun. I'm having fun. I don't know about you guys, but I'm having fun. Okay. All right. Example 1. Example 1 is what type of an example? Arc length. So up there it says a circle has a central angle that is 60 what? Degrees. In this section, degrees good or bad? Bad. Okay. And a radius of 10 centimeters. We want to find the length of the arc that is marked off by that central angle. Okay. So here's the deal. S is what we're trying to find, right? Okay. How about my R value? 10, right? And how about the theta value I need to plug in? Well, it says theta is equal to 60 degrees, right? Whoops. So we better change that. Let's convert that to radians. Yeah, 60 times pi up top, right? And 60 over 180. So I got really 60 pi over 180, don't I? That's what I've got. And the 60 over 180 would reduce to pi over 3. Okay? All right, so are we good to go with the formula to find this arc length in this example? Let's roll with it. My arc length is going to equal 10 times pi divided by 3, isn't it? Okay, let's just see if we all get the same value. So I'll go 10 times pi. I love having this calculator up on the board, by the way. Okay, never mind. Maybe that was weird. You guys getting 10.47-ish? Sweet. So the arc length is how much? What kind of a unit would I choose to put on this? Centimeters, yep. How you guys feeling about this? Pretty good? Just a lot of plugging numbers and going, right? Okay. Sector area then. Example 2, sector area. It says find the sector area of the circle described in example 1. Okay. Okay, so my area here will be 0.5 times the radius squared, which is 10 squared.
Times pi over 3.
Okay, and maybe I need to do a better job here quickly on this second example in terms of what this paragraph says we're leading into this paragraph. So listen up to what I've got to say. We can crunch numbers in a calculator. That's easy. Okay. Help me out, guys. What's the 10 squared? 100. Half of 100 would be?
50.
Do you guys agree that this is really equivalent to 50 pi over 3? Okay, 50 pi over 3 square units. You know what? If you want to leave your answers in terms of pi, that's fine. Okay. Down there at the bottom it says I've expressed the answers using a fraction in radians and as a decimal. It says I want you to leave the answer as a fraction whenever possible. That's kind of in the notes that I've used in the past. You know what? I really don't care what you do. I kind of prefer decimals. What do you guys think? I kind of prefer decimals. I'd like to just crunch this out. We all understand that the decimal has to come from what we have fraction-wise first anyway, right? So if I can get the right decimal, doesn't that imply that we probably have the right fraction in the beginning? Okay, so let's punch this up. Let's go 50 times pi divided by 3. Has anybody gone ahead and done that for me yet? 52.4. And that would be square centimeters, right? So if I have a square centimeter, which is about the size of, trying to find something up here that would be a square centimeter. Square centimeter would be, if this, like that trick? Oh, good one. If I could make a square eraser here, that'd be about the size of a square centimeter. So how many of those are inside of that sector? 52.4. Okay, how you guys feeling about this? Good? Any questions so far? Questions at all? Okay, let's rock and roll. Third page. I like this question, example 3. In example 3, it talks about you having a circle, and it tells you that you have an arc length that is how long? 12 centimeters and a central angle. I like this one because all of a sudden they're measuring this angle how? Radians. It says we need to figure out what the radius is and then use that radius to find the area of the sector. I'm going to make some notes up here. Guys, up top here, they're telling us a sector has an arc length of 12. In the first formula, which is arc length, second formula, which is going to be area of a sector, what does that 12 centimeter arc length represent variable-wise? Which variable up here is the 12 will thickness? So anytime I got problems like this, I say, you know what? I'm going to go through and assign what these values are going to go in for. So the 12 has to be an arc length, and which variable represents arc length here? S does. So anywhere where I see S, what value is going to take that place? 12. Okay. What else do we know?
We know theta.
We know theta. What is theta?
1.25.
Do I have to change that, convert that, or are we golden on that?
We're golden.
Why are we golden?
Because it's in radians.
Oh, I thought you were saying because we've been in the sun too long. All right, no problem. Because it's in radians, I'll take that. All right, that was corny, wasn't it, Caitlin? Sorry.
Yep.
Never mind. I'm done joking. No more jokes. No more jokes. No more jokes.
Say another joke.
Let's figure this first one out, okay? It says the first thing we need to find is the what? Radius. Well, I'm going to use this formula right here. What can I plug in for S, kiddos?
12.
12 is going to equal the unknown radius that we're looking for times my angle in. Can I make a guess on this?
Go for it.
Yeah, 48 divided by 9.6? Yeah. Sweet. Radius is 9.6. What unit should we probably attach to that? Centimeters. It's a length. Okay, centimeters. Very good. Okay, so once we know that, doesn't that allow you to find the sector area up here now? Okay, my sector area then becomes the following. A equals 0.5 times
9.6 squared.
9.6 squared times what?
1.25.
Anybody crunch that out yet?
Yeah. 57.6.
57.6. Okay. So understand something like this. Sometimes they may not say find the arc length. They might say, hey, here's a problem. You need to work backwards. Good to go. Okay? You guys have a great day.